Okay, so how do I make sure that I do not end up over differencing? Then there are couple of tests to help you detect that you are over differencing, but even without using this test, if you exercise enough caution, you can avoid over differencing. For example, keep looking at the ACF, conduct unit root tests before you proceed to differencing. That will by and large avoid this ill step of over differencing. But let us say that I do not know, I have written some automated procedure and so on. One of the simple ways of testing for over differencing is to look at the variance of the differenced series. Okay. If the variance of the difference series is greater than the variance of the original series, then you have over differenced. At least if the given series has white noise like characteristics to you, that is why it is a conservative test. For example, imagine that you had in place of W, like in the previous slide we have Ek in place of Wk, then what do you have here? Ek, what is the variance of Vd? Sorry, what would be the variance of Vd? 2 sigma square E. Are you planning to cancel out the variances? Okay, correct, that is the correct position like this, right. So, perfect, at least the reaction is perfect. So, the variance of Vd is 2 sigma square E, whereas the variance of the original series is sigma square E, right. On the other hand, if truly in place of Vk you had an integrating process, then differencing will reduce the variance of the series. At least you can look at it from a sample variance viewpoint, right. For example, I do not know, let us go and look at what happens here. So, let us say I have here an ARIMA process. So, I am simulating an AR1. Let us look at the sample variance, I am not looking at the theoretical variance. So, this is the sample variance, right, very high. In fact, if you also look at the periodogram of Vk, you will find this is a typical characteristic of an integrating process or a near integrating process, because I do not know how many of you remember even from your electrical engineering background, integrators are this ideal low pass filters, you recall. So, this integrator is an ideal low pass filter, it has allowed only low frequencies to go through, and therefore, the series has predominantly low frequencies. Predominantly does not mean that others are not there, but it just overshadows everything. Now, if I look at the variance sample variance of differenced series, what do you expect? Do you expect to shoot up or come down? Right, drastically it should come down, because what have you done by differencing? That is why the filtering perspective is just beautiful, and I am slowly sowing the seeds for frequency domain. So, we have already argued that differencing operation is a high pass filtering operation. That means it allows only the high frequencies to go through. Therefore, what have you done here? You have taken a process which predominantly has low frequencies and passed it through a high pass filter. What does the high pass filter do? It takes out the low frequencies, it just says you are not allowed to go in, only people with these ID cards are allowed to go through, right. As a result, now the differenced one has gotten rid of the integrating effect. So, look at this, the same operation that you have been looking at it from an integrator and differencing perspective. Now, we can give a frequency domain flavor to it. Now, you can also look at the periodogram of, and I promise it is going to look a bit crazy, but it definitely not going to look as clean as this showing heavy low pass low filtering characteristics. Now, what do you see? You see all frequencies contributing to the power, more or less. Theoretically, you can show that since we have taken a pure integrating process, we will show theoretically next week that what one should expect is a flat spectrum for the differenced series. Okay. Now, what I can ask you to do as a homework is go back and create an integrating process of order 2. and see how gradually the differencing operation is slowly taking out the integrating effects. Okay. Of course, do not do the reverse mapping, that is always when you see low frequencies predominant that you have an integrating effect, but at least there is a strong case for differencing, that is something that you can keep in mind. Okay. So, the other test that is available is the test for unit root in the moving average polynomial. This is also widely used, and there are some tests that are available. I am not going to go further into in detail on this aspect, but this allows you to do two things. One, test for over differencing. If you have over differenced, what have you actually done? You have introduced an artificial 0 at a unit circle or at unity, and that is what this test will tell you. And remember, we said we can also use differencing to handle trends. Suppose there are no integrating effects, but you found a trend, and let us say you did not pay attention to the trend, you just looked at the ACF, and we have seen this earlier. When I have when the series has a trend, the ACF decays very slowly in that case also, and without looking at the series in a rush, you simply went ahead and differenced it. And we have said that earlier, that is not the correct way to do it, because it introduces an artificial 0, unnecessary 0 at a unit circle or at unity, and this test can be used to distinguish therefore between a series with integrating effects and a series that has trends. So, coming to formal tests for unit roots, right, and now we are talking of unit roots in the sense poles on the unit circle. There are in the literature many, but among which 3 are quite popular: the augmented Dickey-Fuller test, and the Philippe-Perron test, and the KPSS test. I am not going to read out the authors' names, but there are a few other tests also available. These 3 tests are coded in R. You have ADF dot test, and then you have PP dot test, and then you have KPSS dot test. So, for example, here we can quickly run the ADF test on the series that we have created. I am sorry, I did not increase the font size here. Okay. So, we can run an ADF. In fact, you should look up the help on ADF test, right. So, if you look up the help on ADF, it says computes the augmented Dickey-Fuller test for the null that X has a unit root. Whenever you conduct a hypothesis test, make sure you are clear what the null hypothesis is. It may be counter to what you think. So, here the null hypothesis is that it has a unit root, and going by the p value, the significance level you can set. For example, here probably the significance level is set to 0.05, but it does not worry about the significance level. It says I will give you the p value, you set your significance level. If the p value is less than the significance level, then what do I do? Reject the null hypothesis. Remember, if the p value is low, the null hypothesis must go, right. So, you set your significance level after the p value is obtained and figure out if the null hypothesis is to be rejected. But you should also look at the alternative. It says the alternative is that to be one of stationary or explosive. Why these two alternatives are given? Yeah. So, because the integrating process is not an explosive series, although its variance seems to change with time, but because of the nature of the mean non-stationarity, it does not run away from you, but it is not stationary either. It is like a cat on the wall, and in the deterministic world such processes are called marginally stable processes. We have integrating process even in the deterministic world. In the systems theory language, it is called, these processes are called marginally stable processes. They are just marginally stable, they do not belong to either category. So, the integrating process is neither stationary nor is it explosive, and now you want to test this null hypothesis that it is integrating against one of the two alternatives, and the two alternatives that we have are is that it is stationary, that means the pole is well within the unit circle, and the other alternative is that the pole is outside the unit circle. That is how you can look at. So, the default is stationary, it says that, right. So, let us ask here, let us ask the test what it has to say for Vk. What do you expect? Come on, this at least you can say, you know, we are the creators of Vk. What do you expect the result in terms of p value, let us say? Always when there are two options, there is a division. What is the null hypothesis? 0. No, pole at a pole at unit circle. Does Vk, has Vk come out of the process with a pole on the unit circle? Yes. So, what do you expect for the p value, low or high? That is all, you just have to think logically. Do not think that you are in a pressure cooker and you have to go bang here and there. What do you say of the p value, what do you see? Very high, very high in the sense does not matter high or very high, but generally the significance levels that we choose, the alpha, which are the type 1 errors, are 0.05 or 0.01, and the p value is higher than that, which means there is no evidence to reject the null hypothesis that it comes out of a unit circle. Obviously, you will be curious to know what does it have to say about the difference series. What do you expect now the election result to be? Right? So, now it is 0.01, and typically if you choose alpha as 0.05, then you have to reject this null hypothesis. Of course, it just sits on the borderline there, alpha equals 0.01, but the p value has to be lower than your alpha, it cannot be exactly equal to that. Anyway, this is the way you formally use a unit root test, and the ADF test has its own demerits, and as you can see chronologically, the ADF test came earlier, and then the Philippe-Perron test, and then the KPSS test. So, people have been busy doing their PhDs on these kinds of problems, and subsequently also a few other tests have come about. The KPSS test can be used for detecting unit roots in presence of deterministic trends as well. So, let me very quickly go through, take a couple of minutes and estimate, go through this example of estimating an ARIMA model, and then I will conclude with variance stabilizing transformations that will end the non-stationarity business. So, here is a simulated series, and we want to see what it means to fit an ARIMA model, what are the things that we have to watch out for. We have seen this kind of plots before, simulated series, ACF showing very slow decay. So, there may be a possibility that there is an integrating effect. Of course, you can run the unit root test, I am not doing that, that is a simple exercise for you. The PACF shows that yes, there are autoregressive effects, and if you were to fit an AR1 model, it says the PACF at lag 1 shows that you may end up with a pole on the unit circle. But if you were to fit an AR model for the given series, what is the order that it is suggesting? Third order, right? It is suggesting third order. There are 3 significant ones, at least to begin with. So, we fit an AR3 model, and here you have the AR3 model. Let us look at the residuals first and then come back. The residuals of the AR3 model suggest that the residuals are white. So, we can go back and look at the errors in parameter estimates. Here are the errors in parameter estimates, and they are all fairly low to the extent that all the parameters that I have, estimates that I have, are significant statistically. Sigma square E is given to you. I have not told you what the underlying process is here, straight away I started with the series. So, we will keep that as a suspense, right, that because that is what is close to reality. Now, I fit an AR model, although I say ARMA model, I fit an AR model. So, this model is satisfactory in almost all respects, I have not cross validated, but this is one model that I have. The other option is to difference the series, because I saw, let us say the unit, the formal test gave me, let us say that it says that there is evidence, and I went ahead and I difference the series, and you can see now the slowly decaying ACF has been replaced by an ACF of a typical stationary process, and the PACF suggests that I can fit what kind of a model to the difference series? second order AR, or I can fit an MA also, right. Either way is fine. So, let us say we fit an AR2 model, and in the end I have also what I have done is I fit an AR2 model, I have also fit an ARMA model, both have the same number of parameters, right. Now, which one do I choose? These are the models for the differenced series, please remember that. Which one do I choose? Now, you can apply AIC to these two models, you can look at one such criteria, but we will pick, I am not applying any AIC, just for the sake of illustration we will select AR2 primarily because you obtain unique estimates, that is one reason. The other reason is you can see sigma square E is lower, always your estimate of sigma square E is a reflection of how well you have managed to predict or capture the predictable portion. Why? Because sigma square E is the variance of the unexplained part, always, because it is a variance of what you cannot predict. And with AR2 I have sigma square E lower than ARMA 1 1, which means AR2 has done a better job of explaining the given series. So, we stick to AR2, and I am just showing you the ACF and PACF of the residuals from the AR2 series. Therefore, the final model that we have with the differencing approach is an AR3, but one of the poles fixed to unit circle, other poles are here. So, now the question is I have two models, I had an AR3 for the original series and AR2 for the difference series, which one is better, and that is the final thing. Now, it turns out that when I look at the poles of AR3 model, you can see that all the poles are well within the unit circle, no problem, it is stationary, whereas obviously with the poles of the integrating this ARI model, one pole is at the unit circle. Now, which one do I pick? We will pick the first one because the point estimate is stationary. What about the confidence regions? Now, it turns out that if you work out, there are many possibilities now. See what you have to see is there are 3 poles for the AR3 model, and likewise you will have confidence region for each of those 3 poles. It turns out that if you pick one of the combinations, it turns out to be non-stationary. And once again, using the arguments that we used earlier, we reject this AR3 model in favor of the integrated process, that integrated approach, that is the AR2 and integrated model. So, the final model that we choose is this one here, the second model H2, although the data generating process does not have an integrating effect. It has very close to integrating effect, but estimation errors have forced us, estimation aspects have forced us to live with an integrated model. But again, it depends on the method that you use to estimate these parameters. If your method is very good at estimating poles very close to unit circle, then you may not have to difference a series. If it is able to estimate poles with really high precision, then you are okay. But in this case, I have used a method that perhaps has not done a great job. So, you should remember this thing. I will just take couple of minutes on non-stationities and then we will adjourn. So, that kind of concludes the integrating effects thing. Now, the last non-stationarity that I wanted to very briefly discuss is that of heteroscedasticity. It is a big word, it takes some time to pronounce it, but that means it also tells you it is a complicated process. So, the heteroscedasticity term is used for processes that have changing variance, whose variance changes with time. You may say, well, the integrating process also has that, right. We have also already shown that the variance of the random walk process changes with time, but and yes, that is also a heteroscedastic process, but there is something else about the integrating process that required special attention. On the other hand, you do not have to have integrating effects, the mean may be changing in a different way and the variance therefore may be changing in a different way. So, the class of processes whose variance changes with time are called heteroscedastic processes, and you will find numerous such processes in econometrics and to a certain extent in engineering and in nature for sure. So, there are two possibilities. Variance can be a deterministic function of the mean, that in many processes the variance may be coupled with the mean. For example, if I take a Gaussian process, is variance coupled with the mean? No. What about a Poisson process or What about the Poisson process? Do you think the variance and mean are coupled? Yes. So, non-Gaussian processes can have that kind of a characteristic, right, or it could be a very complicated function of the series. Now, generally one has these two approaches, one is the variance stabilizing transformation and the other is to build what are known as arch models. Either you work with transformed series to get rid of the variance changing with time, or you work with a generalized set of models, another class of models known as the arch or Garch models. Arch models I have said earlier, autoregressive conditionally heteroscedastic models. Now, that is a lot, that means we will not discuss this in the course, but you should be aware and they are very, very popular in econometrics, and Garch is a generalization of that. We will not go into that. I just want to quickly go over the variance stabilizing transformation. So, assume that your variance is some function h of the mean at any time, and what you want to do is you want to find a transformation that such that the transform series has a constant variance, that is the goal here. So, let us say that transformation is G. What we do is to figure out which transformation will get rid of the dependence of variance on the mean. We construct a first order approximation using Taylor series expansion and essentially write G of yk as first order, construct a first order approximation of G of yk around the mean, local mean, and that is what you have in equation 14, and what we want is the variance of G of yk to be independent of the mean or independent of time, it should be constant. Now, you can evaluate the variance of G of yk. On the right hand side you have variance of two terms, sum of two terms. The first term is a constant G of mu k, at k it is constant. So, you are left with only the variance of the second one. Remember, adding constants do not change the variance. So, when you work out the math, it is a very, very simple math. You find that the resulting transformation, whatever transformation you are planning to use, should satisfy this result. If you know h, which is the dependence of variance on mean, it says you can figure out what the transformation is, and that is given in equation 15 here. And from this came about the more general class of transformations by again Box and Cox. You can see Box appears everywhere, and also the equation is in a box there. So, the general set of transformations that were suggested by Box and Cox, they are known as Box-Cox transformations, and there is a parameter lambda to control the nature of transformation that you do. For example, if lambda is 1, you are simply inverting the series 1 over Vk, and if it is minus 0.5, you are actually inverting the square root of the series, and if lambda is 0, then you will be taking a logarithmic transformation. Remember, logarithmic transformations are used, for example, which have a growth type of characteristic to the process. So, generally you should remember that these kind of transformations, one, are valid only for positive valued series, and this transformation can aid even in improving this Gaussian approximations or Gaussianity that we are working with. Remember, we said Poisson process can have or even an exponential process can have mean and variance coupled. The moment you take this transformation, you are improving the distributional characteristics. So, I will just conclude with an example from Shumway and Stauffer. There is a series called VAR, which is essentially the deposition of the sand and silt and so on in a certain location in Massachusetts in US, not in UK, over a certain period of time. If you were to plot the VAR series over so many years, you can see that there are locally variances exploding, right. The variances are actually changing with time, but this is not an explosive series as such. So, it is a stationary process in that sense, but the variance is changing with time. On the other hand, if you take, in fact, if you look at the histogram of VAR, it has a chi-square kind of distribution. It does not have a Gaussian distribution. On the other hand, if you take the log, then you see that the variance has stabilized more or less over different segments of the series, the variance is kind of uniform. And finally, if you look at the histogram of logarithm, it is Gaussian. So, you have to be careful also. This means that if your series is Gaussian somehow and the variance is changing with time, it is possible, or whatever it is, when you are transforming the series, you may end up changing the distribution, and therefore, you have to be careful in working with these transformations. Anyway, so we will not go beyond this. This concludes the discussion on non-stationary series. We will in the next class start off with Fourier series. Okay.